All right, here in the P6 video, we are going to talk a whole lot more about imaginary numbers and what happens with all of those. So, imaginary numbers are a part of what are called the complex numbers. It is an extension to the real numbers to create a larger number system. Real numbers are always going to be complex, but complex numbers can't always be real. Well, let's talk about why. Why do we even need complex numbers? Where is it coming from? And why does these statements make sense? So if I try to graph x squared plus 1, we know it's going to be a U-shape, and we know that it's going to be up 1, translated up 1 because of the plus 1 for a y-intercept. Now, if I want to get other points, I could plug in an x value of 1 and see what the y value is to create some ordered pairs. So if I plug in 1, I'll get 1 squared plus 1. 1 squared is 1, plus 1 is 2. That means when I plugged in 1 for x, I got 2 for y. And parabolas have the points on both sides that are reflective. So that means if I were to plug in -1, I should also get +1 because I'm the same distance away from the vertex. Then I'm going to plug in 2. 2 squared, 4, plus 1 is 5. So if I plug in 2, I get out 5. Same thing if I plug in -2. -2 times -2 is 4. 4 plus 1 is 5. Shows us why those reflection points exist. So we've got our parabolas here. But when I look for the zeros, when does it actually equal 0? I'm not getting anything. That when we solve this, we actually wouldn't be able to get something. So if I subtract 1 from both sides, x squared is equal to -1, and I take the square root, x equals, I'm using a square root while solving, I need the plus or minus. Square root of a negative triggers an I, and the square root of 1 we know to be 1, 1s are irrelevant. So we just have x equals plus or minus I. We see that if algebraically we were to solve for it, we don't actually get a number that we can graph. This is where the imaginary numbers are coming from and why we're going to get answers that aren't real for some parabolas. So complex numbers have two parts. They have the real part and the imaginary part. A part that has an actual number and a part that has a section with I. They've got the two different parts here. So if I were to look at this and try to match up the parts, this is the A. This is the real part. And then the B is the number in front of the I. So that's where I will get -4. So 2 is A, -4 is B in this case. The nice thing about this is that when you're adding and subtracting and you're thinking like terms, we can only combine real parts with real parts and imaginary parts with imaginary parts. So it's kind of like the combining like terms you've been used to. That here the 2 and the 4 are like terms, that when I add those I get 6. And then the 3i and the -i combine together to give us a positive 2i. Same thing here with a subtraction. We just got to be a little careful of making sure that we incorporate this negative sign. So something I will recommend is to write it like an addition problem where you're distributing that negative out. And then you'll be able to see that we've got 2 and -4 combining to be -2, and then a 3i and an I coming together to be a positive 4i. Multiplying, it's just distributing and combining the like parts. It's kind of like foiling all over again. So 2 times 4 will give us 8. 2 times a -i, a -2i. 3i and 4i will become a 12i. 3i and a -i will become a -3i squared. Here's the thing though, we have to remember something special about I squared. I squared is equal to -1. Maybe you remember that, maybe you don't, but that will help us as we solve. So here I've got my I terms that are alike, Negative 2 and 12 will give us a positive 10i. Drop down the 8. But because I squared is like negative 1, this negative 3 is really being multiplied to negative 1. So that means I'm actually adding 3. So negative 3i squared becomes a positive 3. 8 and 3 are now like terms, so I will get 11 plus the 10i. Same thing here, but this is something that is special. It has what's called a complex conjugate. Conjugates are numbers that have the same thing on the left and the right side, but what separates them is the sign between. So the complex conjugate, I apologize, I wrote that wrong, is going to be a minus bi. So the plus and the minus is what's different. Just like up here, you see the plus and the minus being different. So 2 times 2, 4. Foiling out something I feel like you guys are good at gives us something that looks like this. And what happens with these complex conjugates is the middle part always drops out, that we've got a negative 6i and a positive 6i that are going to undo each other. So I've got a 4, but my minus 9i squared. Remembering that minus I squared is negative 1, it's really negative 9 times negative 1, or a positive 9. That would tell us our answer here is 13. So then here, if I were to look at this, the complex number is a single letter, often called z, not something that you're going to see a whole lot of, but if I were to try to do z squared, that really means that I would want to have the conjugates, that this z idea would want us to have it be 2 minus 3i, 2 plus 3i, and so with this, we would see, I am so wrong, I'm apologizing here, that z squared, same thing twice, that if z is this, there's 2 of them. Sorry, I got confused with what was up here. Ignore what I said about this. If z is this, then z squared would be the same thing twice, that it's squared, so the something times itself. So 2 times 2, 4, minus 3i, or minus 6i, 2 times the 3i, minus 6i. Another minus 6i from the inner. Last, a minus plus 9i squared. Wow, this is not going well. A negative 3i and a negative 3i become a positive 9i squared. Negative 3 times negative 3, 9. I times I squared. So then these are going to combine to be a negative 12i. Drop the 4. Positive 9i squared. So a positive 9 times a negative 1 becomes a minus 9. New set of like terms, negative 5 minus 12i for the answer. What's different here is that now we've got the conjugates. That if I start with a z and then I have this z bar, it means tell me what the conjugate is. So if the conjugate is the same thing, that the 4 and the 3i are the same, but instead of the minus, now I need a plus. This, I will ask you on a quiz if I'm just saying what's the conjugate, it will say like that. You won't need to do the z bar. And here, if I ask you for this, it'll be in a question that looks more like this. This is just what you might see on, like in a college class. Backside. Dividing is really weird with this. So with dividing, you have to multiply the denominator by the conjugate in order to get rid of it. Because what we saw is with multiplying conjugates, it took stuff with imaginary things and got rid of it. Why would we have to multiply by that then? Because just like how negatives under square roots, we now make i's, or that you can't have a decimal inside a fraction usually, there's just those random rules. One of these is that you can't have I in the denominator. So we're going to multiply by conjugate over conjugate of that denominator to remove the i's from the denominator. And then it becomes a multiplying problem. That here, maybe the parentheses will help you see it, but I'll distribute this out first. I'll get a 6 plus a 4i. But now this becomes a FOIL situation where I'll get the 9. We got a plus 6i and a minus 6i. We know those are always going to cancel each other out. So what really matters is this, the 9, and then this, the minus 4i squared we get. If you can jump to the shortcut, great. If you need to go and write out each individual part, that's okay. But then simplifying this denominator, I'm going to get 9 plus 4. Remember the multiply by -1, which means I'm going to get 6 plus 4i all over 13. If we're going to get really particular about this, I would separate it like this because then it gets it in the a plus bi form of a complex number, but I will personally accept either. This one, little different with it because you have, when you multiply by the conjugate, the 3 minus 5i, it's just going to create a longer thing up top that as you FOIL this out, you're going to get more. So I want you to take a second, pause the video, try multiplying it on your own, see what you get. All right, the final answer should have been -3 minus 29i all over 34, or if you broke it up, -3 over 34 minus a 29 over 34i. Again, I would accept either. If you have questions about that, please let me know. Another thing we can look at is how does this impact the quadratic equation? Let's say I have this one right here. So as I set this up, we know we've got A being 1, B 2, and C is also 2. So negative my number for B, 2, plus or minus the square root of 2 squared, minus 4 times my number for A, times my number for C, all over 2 times my number for A. Simplifying and cleaning this up, -2 out front, +2 down below. With the square root, 2 squared is 4. -4 times 1 times 2 is a -8. So I get a -4 underneath. This is not new. We've done this before. So then we know that the square root of -4 will be 2i because the negative part creates the i, and the square root of 4 is 2, all over 2. And then we can split this up. This 2 divides nicely into both, so I will get -1 plus or minus I. What you'll notice about the quadratic part is that this becomes conjugates. That when you use the quadratic formula, your answer will always end up with conjugates for I. This stuff with the discriminant and the calculator, sorry for the long pause there, I was thinking about what I really needed to talk about in the video. I want you to see that b squared minus 4ac, that number underneath the square root, kind of what are the 3 individual cases that we could get? We could get a positive number, we could get 0, we could get a negative number. Well, we saw that if we got a negative number, it triggers imaginary answers. So we're going to call that 2 complex solutions. If I had a positive 4 instead, we'd be able to just have regular numbers and get 2 different real answers or real solutions. because they only have real parts to the answer. There's no I, no imaginary part. But if it equals 0, if the square root part here is a 0, that doesn't matter anymore. Adding, subtracting 0 does nothing, so all we get is whatever this divides to, one answer. So it is one real solution. The calculator also does things with imaginary numbers. And so with that, I will show you that by person if you need to, but this stuff you don't really need to use a whole lot. We can really do it oftentimes by hand a little bit quicker. So with this stuff, if you would like to see the calculator way, I will show you in person. So see me if you need that. Here are some ways in which imaginary numbers get used. Lots of physics in it. This is just something that I'm going to skip because it's just something that you can see. But here is the homework for P6 that you will do after the P4, P5 quiz.